Okay, this lesson is an overview for lecture 7. In lesson 7, we start off by examining the estimation for population proportions. We have a term, point estimate. And the point estimate is the sample proportion that we denote by p hat. It is the best point estimate of the population proportion. For example, if you look at the Twitter poll problem, it says the Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. Based on that result, find the best point estimate of the proportion of all adults who know what Twitter is. Well, if they did a survey of 1,007 adults, and found that 85% of them know what Twitter is, then the best point estimate, p hat, in this case, would be 85% or 0.85. Although they did not ask for Q, we're going to go ahead and talk about Q. Q hat would actually be 0.15, and I got that by taking 1 minus 0.85. Remember that p hat and Q hat must always total 1. The second thing that we want to discuss is the confidence interval. And the author of the book says that we can use a sample proportion to construct a confidence interval estimate of the true value of a population proportion, and we should know how to construct and interpret such confidence intervals. Okay. So here's a definition that goes along with confidence intervals. A confidence interval is a range or an interval of values used to estimate the true proportion of a population parameter. And then a confidence interval is sometimes abbreviated as CI. And one more term that goes with the confidence interval is the confidence level. The confidence level is the probability 1 minus alpha that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. And the confidence level is also called the degree of confidence or the confidence coefficient. For our class, we will just say confidence level. So what does all of this mean? Well, hopefully by the end of this lecture, it will be abundantly clear. But let's sort of move into some geometry so that we can visualize what's taking place. So a 90% confidence level would be alpha minus 10%. Well, what does that mean? Well, if you go to the right here, where we're talking about a 90% confidence interval, notice that 90% is in the middle, so to speak. Well, if 90% is in this mid-region here, then that means that the tails have to total 10%. If you have 90% in the middle, that leaves you 10% left over. And if you split the tails evenly, each tail would be 5%. Notice that there is, I refer to this as a gatekeeper value, but it's actually called a critical value, to be more technical. And the critical value for a 90% confidence interval is 1.645. That's actually the z-score, 1.645. We could generate that z-score by doing inverse norm of 0.95. That would give us the 1.645. And of course, if this is 1.645 on the right side, to balance out, we would have a z-score of negative 1.645 for the left tail. Suppose you have a 95% confidence level. With 95% confidence level, we have Corresponding values of alpha, that would be alpha minus 0.05. Well, alpha minus 0.05, 0.05 would be the total in the tails. But since this is a 95% confidence interval here, 95% of the area is consumed in the middle region. And if 95% consists of the mid region, then I have 5% left over. And if I split the 5%, then that would give me 2.5% for each tail. And notice that the critical value for a 95% confidence interval is 1.96 on the right side and negative 1.96 on the left side. Now, we could have generated the 1.96 by doing the inverse norm of 0.025 plus 0.95. That would be one way to generate the z-score for the critical value. And lastly, for this scenario, we're going to look at the 99% confidence interval. If I have a 99% confidence interval, then I have 1% that's left over, and if you split that, if you split the 1%, you're going to have 0.005 in the tail region. And notice that the critical values are 2.575 and negative 2.575. I have a feeling at this point, this is still somewhat cloudy to you, but we'll proceed with some examples and hopefully it will become more clear. A 95% confidence interval is the most used because it provides a good balance between precision and reliability. In fact, if you are not told in your problem sets which confidence interval to use, we will automatically defer to the 95% confidence interval. The 95% confidence interval estimate of the population proportion in the Twitter poll would be 0.828 up to 0.872. And by the end of this lesson, you will see where we got this confidence interval estimate. So how do we interpret confidence intervals? Well, if you refer to the highlighted region, and we want to wrap this up with a concise statement, we would say that we are 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion P. Okay, let me go back to the original problem here. Pew Research Center found that 85% of adults know what Twitter is. If we generate a 95% confidence level, then we know that the true population proportion that represents those adults who know what Twitter is somewhere between 0.828 and 0.872. And we're 95% confident that the true proportion is somewhere in between those numbers. 0.85 is probably not exactly correct, but we are 95% confident that the given interval does contain the true proportion. This section here with the diagrams basically just reiterates what I said previously, that if you are using z-scores, remember that if you are at the average, the z-score is 0. And we always split the tails in half. That's why we have alpha divided by 2. Again, in this case, we had a 95% confidence level, which means that the area in this region here is 0.95, which means that our tails would have to total 5%, but if I split those evenly, each tail is 2.5%, or 0.025. We've already talked about the critical values because the critical values are these values that are the gatekeeper values that guard the tail region. The most common critical values have to do with the 90% confidence interval, and the critical value is 1.645. For the 95% confidence level, it's 1.96. And for the 99% confidence level, we have 2.575. Again, we could use inverse norm to generate those critical values. Not all of our confidence levels will be 90, 95, and 99, but these are the most popular ones. Notice that if your confidence level is 90%, your alpha level is 10%, because 90% plus 10% would be 100%. Also, a 95% confidence level would have an alpha level of 5%, because 95% plus 5% would give you 100% under the curve. And the 99% confidence level would have an alpha level of 0.01, because 99% plus 1% would give you 100%. Now remember, when we do the tail regions, confidence levels always have two tails, and we always split the alpha level in half. So if you have a 10% alpha level, you would have 5% in each tail. If you have a 5% alpha level, then you will have a 2.5% amount in each tail. And if you have a 1% alpha level, then each tail would be 0.005. This is just a reminder on how to actually generate those critical values using the TI-84. Again, we would just use the inverse norm. You could put, for example, on part A, remember, if this is the 90% confidence level, I'm going to try to sketch this. It's probably going to appear somewhat crude. Let's see if I can do some sort of a rough sketch here, just for this part A here. If I have a bell curve like this and a 90% confidence interval, here are the tails. If it's 90%, then that means that the area here in the mid region is 0.90. Well, that means I have 10% left over, which makes each tail 0.05. Okay. So how would we generate the critical value? Well, remember, if you use inverse norm, you have to tell the calculator the area to the left of the critical value. So if I want the critical value for this region here on the right, then I would say inverse norm of 0.95. An inverse norm of 0.95 is going to give me 1.645. Okay. And that's equivalent. Now notice in the response here, instead of saying inverse norm of 0.95, I just said 1 minus 0.05. In other words, 1 minus the right tail would give me the area to the left. And you would do the same thing with parts B and C as well. Okay, let's clean this up so we can move forward. Okay. The margin of error. Students tend to falter here because of the algebra involved. The margin of error tells us how far we go from the average over to the critical value. I want to draw that for you. If we have a normal curve and we know the average, and we have a region to the right of the average that goes all the way up to the critical value. Well, this region is called the margin of error. Also, you would have the critical value on the left side. And again, you would have the margin of error in the left region. And of course, the margin of error on the left side would be equal to the margin of error on the right side because of the symmetry of the distribution. To calculate the margin of error, here is the formula. At first, it looks a little bit daunting, but it's not too bad. As long as you know the critical value, which we now know how to find using inverse norm. If you know the critical value, if you know p hat and q hat, and you know the number of data values, you can use this formula to generate the margin of error. Okay, let me highlight the formula here for margin of error. Okay, so example 3, Twitter poll. Again, we found out that through a simple random sample of 1,007 adults that our sample revealed that 85% of adults know what Twitter is. And again, we know that 85% is not exactly correct. But we suspect that if we did good sampling, we should be close to the real proportion. We know that 85% is just a statistic. It's an estimate of the parameter. So let's figure out the margin of error involved at the 95% confidence interval. Well, the critical value for a 95% confidence interval is 1.96. We know that p hat is 0.85 and q hat is 0.15, and the number in the sample is 1,007. So we will input into the calculator 1.96 on the square root of 0.85 times 0.15 divided by 1,007. That gives us a margin of error of 0.0221. If we take 0.85 and subtract the margin of error, 0.0221, if we subtract the margin of error, it would give us the lower end of the interval. And if we add 0.0221 to 0.85, that would give us the right side of the interval, 0.8721. So what does that mean? That means that at the 95% confidence level, we believe that the true proportion of adults who actually know what Twitter is somewhere between 82.97% and 87.21%. As you can see, the p hat that we found from the sample is very important because everything depends on that p hat value. To get the lower end of the interval, we subtracted the error from the p hat value, and to get the upper end of the interval, we added the error to the p hat value, 0.85. I think it is interesting to know that using statistics, we can at least narrow down the true parameter for the number of adults who know what Twitter is in this case. Example 4, a Consumer Reports Research Center did a survey of 427 women, and they found out that 29% of them purchased their books online. How many women in the survey said that they purchased books online? Well, if 29% of the 427 women said that they purchased their books online, we would just multiply 0.29 times 427. And that gives us about 123.83. But as you know, when dealing with people, we always round up. So that means that 124 women in the survey said that they do indeed purchase their books online. Part B says to find a 95% confidence interval estimate of the percentage of all women who purchase books online. Well, if we're going to use a confidence interval at the 95% level, we need to figure out the margin of error. Well, the margin of error is going to be the critical value, which is 1.96, times the square root of p hat times q hat, which is 0.29 times 0.71, and then we divide that by n, which is the number of people in the survey. That gives us a margin of error of 0.0430. So using that margin of error calculation along with p hat, we can generate the confidence interval. The lower end of the interval is going to be p hat minus the error. The upper end is going to be p hat plus the error. To get the lower end, we will take 0.29 minus 0.0430 to give us the lower end, which is 0.2470. And if we add the error to the average, we get 0.29 plus 0.0430. This produces the upper end of the interval. So what does this mean? It means that the 29% is probably not the gospel. It's probably not the parameter. It's just a statistic that we used to get an idea of where to look. But if our sampling is strong, in other words, we have no bias, we randomized the sample, then 29% is probably at least in the ballpark. And using a 95% confidence interval, we now know that the true proportion of women at the 95% level who actually purchase books online is somewhere between 24.7% and 33.3%. Part C says, can we safely conclude that less than 50% of all women purchase books online? And we would say yes, because 50% is definitely higher than the interval, which means that the true value is somewhere in that interval. At least we are 95% confident of that. So we would say yes. Since 50% is well above the confidence interval, we will just say that we are 95% confident that the true proportion of women who purchase books online is between 24.7% and 33.3%, which is definitely less than 50%. Now, finding the margin of error can be a headache at times, and I know that students tend to trip over this because of the algebra. Luckily, the calculator will generate a confidence interval. To generate the confidence interval, we go to Stat, Tests, then we select one prop z interval. Remember, whenever we do proportions, we always use z. So make sure you choose one prop z interval. And once you do that, you're going to be asked to enter some key things. For example, they're going to know the X value, which is the number of people who answered in the affirmative. In this case, we had 124 women who said that they purchased their books online. So the X value would be 124. The number in the survey or the sample, 427. And this is the important part, the most important part, because this is the part where people tend to do damage. When you enter the confidence level, and the problem said that we needed to use a 95% confidence level, make sure that you are putting 0.95. Do not put 95. If you put 95, you're going to get some really crazy answers. So use 0.95 for the 95% confidence interval. And then, of course, once you enter that information, just select calculate. And as you can see, we get pretty much the confidence interval. So let's go back and verify that once we put that information in, that we do get the same thing that we got up here, right? 24.7% and 33.3%. Okay. Of course, the example here led to this number here. I got a little off track there, got a little confused. So hopefully that's clearer now. Example 5 is what we just did. The last two problems, since it is political season, let's go ahead and talk about tattooed Democrats. We're looking for the appropriate sample size. Well, here's the formula for the appropriate sample size. This is telling you, in essence, how many people you need to survey in order to have a robust study or a robust sample. Where did this come from? I generated N by going back to the margin of error formula, and I solved for N. In other words, I got N by itself using algebra. Once you solve for N, this is the formula that you use to determine the appropriate sample size. So example 6 says, find the sample size needed to estimate the percentage of Democrats who have tattoos. Use a 5% margin of error, use a confidence interval of 99%, and use results from a prior Harris poll suggesting that 15% of Democrats have tattoos. So if 15% of Democrats have tattoos, at least according to a recent poll, then we will use the p-hat value of 0.15. Well, if p-hat is 0.15, then q-hat is 1 minus 0.15, which is 0.85. Then we divide by the margin of error, which is 0.05, over the z-score, the critical value. The critical value for a 99% confidence interval is 2.576. And again, we could get that from inverse norm. Then you're going to square that denominator. And once you do that, we get, after rounding, 339 people. So if you would like to do a study with a 5% margin of error at the 99% confidence level, you would need to include 339 people in your sample. Example 7, Republicans. Find the sample size needed to estimate the percentage of Republicans among registered voters in California. Looking for the percentage of Republicans among registered voters in California. This one says to use a 0.03 margin of error, and we have a 90% confidence level or confidence interval. And it says that p-hat and q-hat are unknown. So they did not give us any point estimate here. If they do not give you a point estimate, you just split it in half and you let p-hat be 50% and you let q-hat be 50% because that's really the best you can do. So this would be p-hat times q-hat. This is the margin of error. This is the critical value at the 90% level. Of course, you square this and you get 752. In other words, at the 3% margin of error and a 90% confidence interval, you would need to survey 752 individuals.